Welcome to note set number 23. In this video we're going to be talking about how to use the DTFT to analyze discrete time systems, and we'll be focusing on non-periodic signals. To be honest, periodic signals don't quite show up that much in discrete time system analysis. As we saw in the continuous time case, the Fourier transform handles the periodic case as well as the non-periodic case. So we'll pretty much just focus on the non-periodic case here. So as I mentioned last time, for a continuous time system, if it's a circuit, we already know how to find the frequency response. But for a discrete time system with a difference equation, we don't know how to do that yet. So let's spend a little time figuring out how to get the frequency response. And remember, this will play the same role that we had for frequency response of a circuit or a continuous time system. So even though, let me say it this way. When we were analyzing circuits, the way we got to phasor analysis is we said, let's see what happens when I put e to the j omega t into my circuit. And we analyzed how that worked. Well, we can do the same kind of thing, except now we have to have a discrete time complex sinusoid that we put in. And we hypothesize, based upon the fact that we think discrete time systems should be similar to continuous time systems, that we should get the same kind of thing out, that we should get some h of omega, a complex number that multiplies the same input complex sinusoid to provide a change in amplitude and phase. So we put in unit amplitude and zero phase, and we get out something that has some potentially new amplitude and some potentially new phase. So we should be able to do the same kind of thing. So if this is the input and this is the hypothesized output, they should solve this difference equation. So, and by the way, that should be a lowercase y. So let's just plug these things in and see what ends up happening. So when we plug that in, this we get y of n. So there it is. We plugged in our hypothesized y of n. Now we're going to plug in y of n minus 1. Well, where does that happen, right? There's the n, so we get n minus 1 all the way down to n minus n. And the same kind of thing on the x side. We're going to plug in this e to the j omega n. There we get an n minus 1 all the way down to n minus m. Okay, good. But now we see that with a property of exponentials, we can take this thing and rewrite it as e to the j omega n times e to the minus j omega. And we can do that for every one of these terms and have this e to the j omega n term. So we can pull that out in front, and we'll have the same thing over here. And hey, if it's on both sides, we can get rid of it, right? Good. Okay, so now we've also got this h of omega, which was common. And so that got pulled out. So now we just need to solve for h of omega. So that means taking this in the numerator, putting this in the denominator, and there's our result for h of omega. Now, do we have to go through this rigmarole each and every time we want to find h of omega? No. Look, we can write it by inspection. B0, B1, all the way down to Bm. Just go in the numerator with the appropriate e to the 0, e to the minus j1 omega, e to the minus j2 omega, all the way down to e to the minus jm omega. So whatever coefficient index we have, that's the integer that multiplies the minus j omega. Same kind of thing. We go over here to our coefficients. We've got 1. We've got a1, e to the minus j1 omega, all the way down to an, e to the minus j omega n. So you give me the difference equation, I can immediately write the frequency response. And that is great. You show me this difference equation and say, here's my discrete time system. Bam! there's my frequency response. I've got it that fast. Now, we've just shown that is true. We've established that. And by using Euler's formula and linearity, we can break this into two of these things. And we can then show, again, this should be lowercase. This should be lowercase. Sorry about that. And we can show the same kind of thing that we saw for continuous time, that for a real valued sinusoid, the frequency response works magnitude out front to modify the amplitude and angle inside to additively modify the phase. So this tells us that if we put a real sinusoid into a discrete time system, two things happen. The amplitude of that sinusoid gets changed multiplicatively, and the phase gets changed additively. Both of those factors determined by the frequency response evaluated at the frequency of the sinusoid. Okay, very nice. Now, here's an alternate way to find that frequency response. It's a little more straightforward, but it doesn't get tied to this idea of putting in a sinusoid. But nonetheless, it proves the same thing. We've got a discrete time difference equation. It's an equality. I can take the dTft of both sides and I'll still have an equality. So if I were to do that, apply dTft to both sides, no problem. Now I use linearity and pass the dTft through, but I also use the delay property. The n-1 gives me a minus j, n minus n gives me the minus j omega n, and so on. Now I play the same game. I pull the y of omegas out, pull the x of omegas out, and I get something that looks like this. Now remember, h is the thing that I multiply x to get y. So here's y, here's x. If I take this and bring it over as a denominator, I've got h. And so that's what I've done in this step. I show this thing being brought down into the denominator here, and aha, there's x times some big thing, that's h, to give me y of omega. And this is exactly the same result that we saw in the previous method. So we now have seen two ways to verify that this is the way that we find the frequency response of a discrete time system. Now, if we recall the definition of frequency response, this is how we found it just a few minutes ago. You put in a sinusoid, and out comes that same sinusoid, but with a complex number out in front telling us the new amplitude and the new phase of that sinusoid. Okay, but now imagine that I've got some x of n. The inverse dTft is telling me that I make that up by integrating up a whole bunch of different components over all the different frequencies from minus pi to pi. And what are the individual components? They look like that. So each one of those components, how does it go through my linear time invariant system? Well, each one of them gets hit by the h of omega at its corresponding frequency. So h of omega times the thing that went in gives the response to that one component. I added up all these components from minus pi to pi. I'm going to add up all those components from minus pi to pi. Bingo, I've got it. And now we notice that this integral is just an inverse dTft of what? Of that. So that must be the output signal's dTft. So once again we see that y of omega is equal to h of omega times x of omega. This is the equation that links the input Fourier transform to the output Fourier transform, and that h of omega is called frequency response. And just like we saw for continuous time case, this frequency response allows us to visualize what a system does. What frequencies does it boost? What frequencies does it cut? That comes from this magnitude relationship. Also, how does it change the phases at each input frequency? And that comes from this relationship. But to be honest, it's the magnitude relationship that plays the primary role. We can't ignore the phase relationship, but we do need to keep track of all that. So in general, what we're seeing, same kind of thing. I'm just stealing these charts from the continuous time case and reworking them for discrete time. Discrete time LTI system, through its frequency response, will emphasize some frequencies, de-emphasize others. Some frequencies it may just leave untouched, same amplitude out as it went in. So this is really the big idea. So we now know how to use the DTFT to do general system analysis for discrete time, linear time invariant systems, and that's a really big idea. So these are the two different ways that we've just talked about using discrete time or using frequency response to analyze discrete time systems. Now there is a way to use this for periodic signals, but I'm not covering that. We can handle that just as easily through generalized DTFTs. But the point is that if we've got sinusoidal input, you can do it directly using that formula, modifying amplitudes and phases directly. If you've got some arbitrary input, you need to know it's DTFT, multiply it by the frequency response, and if you want to get the time domain signal, take the inverse DTFT. However, most of the time, what we're really interested in is just thinking about h of omega. So this equation, we're not really doing it that much, we're thinking it. Okay, h of omega times x of omega, take the inverse DTFT. But what we're really doing is just looking to see what frequencies does the system boost, what frequencies does the system cut, those kinds of things. So let's take a look at an example. Ideal low-pass filter for the discrete time case. And we will see that we really cannot build such an ideal filter, and it'll be the same reason for why we couldn't build an ideal continuous time filter. So here's our specification for an ideal low-pass filter. This should be on the omega axis. I don't show that there. Now notice that unlike in the continuous time case, when we show DTFTs and we show frequency responses, and really a frequency response is a DTFT. It interacts with a DTFT, so it has to act like a DTFT, and in fact it is a DTFT. So it will have this repetitive nature, this periodic nature. So we're showing all the periodic parts out here as well. But remember, we focus in the minus pi to pi, so you can kind of ignore those until you need to think about them. But we can focus on the minus pi to pi. The B shows the cutoff frequency, B radians per sample for the discrete time case. So this is illustrating how we might use such a low-pass filter, and I'm still idealistic, thinking that I can have an ideal filter here. In a practical world, we can't implement an ideal filter there, but for the moment let's just think about that maybe we could at least in principle have an ideal low-pass filter there. So suppose we have some signal x of t, and here's its DTFT, or I'm sorry, CTFT, that's outside of the A to D converter. Then we go through the A to D converter, and here, again, we're being idealistic. Critical sampling, so that we're sampling right at that point and we have no gap here. We see the replicas. Then we apply it to this ideal low-pass filter with a cutoff of B. So we're only passing the part in the center, and this part gets zeroed out. But notice what happens. All the replicas have to have the same thing applied to them. That's an important thing to remember. Since we often just focus on that minus pi to pi part, we often forget that, but you should keep it in mind. So the part inside here gets filtered. These things also get filtered. They have to, because this has to end up being a true DTFT, which has to have this periodic nature. But the idea here is that we've cut certain frequencies using a discrete time system. And so then we go through the DAC, assuming ideal reconstruction, everything's beautiful, everything's perfect, and now we get back something that looks like it's gone through a continuous time system. So it's as if we took this continuous time signal spectrum and we modified it by multiplying by a continuous time system's frequency response. Now, again, a lot of idealities here, but the idea holds. That's why today it's very common to take a signal, sample it, bring it into a discrete time system, a computer, FPGAs, things like that, implement some discrete time, linear time invariant system, and then put the signal back out. It happens all the time in your phone, happens all the time in your iPads and on your computers and things like that. So this is a very powerful way of doing things. So let's look at a simple non-recursive filter. I say it's non-recursive because we notice that there's only one y term, so there's nothing over here that's being fed back. We don't really need to solve it recursively. As soon as you tell me two successive input samples, I can tell you what the output is at that instant in time. I don't need to know what happened previously. So there's no recursiveness to this. And we'll talk more later about recursive versus non-recursive filters. So if you compare this to that general block diagram that we had in the previous lecture, you should be able to see that all those feedback paths have been set to 0, and we just have these so-called feed-forward paths with the coefficients of 1/2 and 1/2. So this block diagram shows how you might implement this in an FPGA or something like that. But it also helps see how to do it in software as well. So our general results for the difference equation and frequency response are reiterated here. And remember, all we have to do is just look at the coefficients here and we can write this down. Look at the coefficients here and we can write this down. So let's do that for this simple case. Notice that for us, we don't have any of these things, so all we have is a 1. So the entire denominator reduces to 1. So we don't even really have to think about it. And up in the numerator, what do we have? We have a 1/2 and we have a 1/2. So we have these two terms with a 1/2. Factor the 1/2 out in front. There's our frequency response for that discrete time system. Now, I'm claiming that this is a low-pass filter. Let's take a look and see if we can establish that that is true. Okay, so we've seen this before. The math is very similar to the case for the continuous time system with the acoustic response of the room. So the math is very similar to that. What we do is use an Euler formula to convert that complex exponential into a cosine, and then into cosine and sine. Now we have everything in rectangular form, so we can add it. We have a real part, imaginary part, grouped cosine squared and sine squared together. That ends up being equal to 1. And so we see that this is the magnitude response. And if we look at that, we can see that this thing is actually going to give us a low-pass filter or not. So if we plot that, and again, remember we're focusing on the minus pi to pi region, what we see is that, well, yeah, okay, it is sort of a low-pass filter, but not a very good one. So we can think of, low frequencies are kind of being passed and high frequencies are kind of being cut, but it's really not a very good one. So how do we make a better low-pass filter? That's a good question. So we could try doing taking this idea to a longer type of this filter. We had two terms and we had 1 over 2 in front of each one of them. So in a sense, what this filter is doing, if we go back and look at it, what the filter is really doing is just taking two adjacent terms, adding them together, and dividing by 2. So it's like computing the length 2 average and letting kind of moving window through the input of length 2, always averaging 2 samples, 2 samples, 2 samples. And so yeah, that kind of makes sense that it smooths out any large rapid fluctuations. But now we could take n samples, n successive samples, add them together and divide by n. So it's kind of a moving average of order n, and we could look to see how well that works. And we see, well, actually not all that great. So we can easily write out what the frequency response is mathematically, and we can then calculate it in MATLAB. And we see that as we increase the length of this, so this is the number of samples that we use in this moving average, we end up making a narrower and narrower low-pass filter to the extent where we're using n equal to 20. We've got this really narrow pass band, and the stop band is not all that great. So these are actually pretty crappy low-pass filters, but nonetheless they are low-pass filters. So in the time domain, this idea kind of makes sense. You got a lot of wild fluctuations. Oh, just kind of smooth it out with some localized averaging, that you move this averaging along. Well, we see that this really doesn't give us a very good low-pass filter at all. So we need better ways to do this. Here's a way that we can, in general, compute the frequency response of any discrete time system. So we're leaving behind that idea of how to design a good low-pass filter till later, and just touching on kind of a general purpose tool here. So this MATLAB command called freqz allows us to compute the frequency response of for a given difference equation. So yeah, it's easy by to just write down by inspection what that equation is, but then you still have to program that all in and get MATLAB to take absolute values and things like that to get the plots. Whereas here, all we have to do is take all of these a coefficients and put them in this vector, take all these b coefficients, put them in this vector, and then give it a w vector that tells it what frequency do we want to be able to compute this over, and it will compute the frequency response at all of those frequency points. So let's take a look at an example of using this here. So here's a simple difference equation. We've got our output side and we've got our input side, and yeah, by hand we could say, all right, I take the 1 and the 1 and I make the numerator. I take these coefficients and I make the denominator. Okay, there's what I theoretically have, but to compute it and plot it, it's very easy. First, we create a linearly spaced set of points from minus pi to pi, and I chose to take 2,000 of them. You could pick other numbers there, and there's pros and cons to what you pick. Obviously, the bigger number that you pick, the closer the spacing is going to be. So you want them fairly closely spaced, so you want to make this a fairly large number. Then we take our 3a coefficients and we put them in here. We take our 2b coefficients and we put them in here, but notice that in reality, we've skipped a term, right? We've got n and n minus 2, so we have to have that 0 in there to account for that skipped term. Then we take these three things, we take their symbols, put them into freqz, and the rest is just plotting absolute value and plotting angle using those MATLAB commands. And the subplot commands put two plots on one plot. And then I did some other formatting that I'm not showing here, like labeling and things like that. Um, now here's a filter that, it's not a great low pass filter, but it is passing things down here. In fact, it's accentuating some, and frequencies from pi over 2 up are being suppressed relative to those at the lower frequencies. So we'll explore much more about how to get different discrete time filters. So just recalling for the moment that non-recursive filters have no feedback. So their difference equation has only a single output term over there, and the frequency response immediately can be written down by just taking those coefficients and writing it like that. And that kind of filter, here's another, here's a low pass filter that I made with just doing a 1, a 2, and a 1. Still not a great low pass filter, but not a bad one. So these things are easy to play around with, but we'll see later on some very high performance ways of designing some really awesome filters using some design tools that are built right into MATLAB. Thanks, and I'll see you next time.